Let's go back to the one slide that I described earlier in this lecture that captured the key features of this course. We have a structural system, a simple prismatic bar subjected to axial tension in this case. In a more general case, we could have instead an IC interconnect, a gas turbine blade, an aircraft landing gear, or a tall building with thousands of degrees of freedom subjected to seismic loads. Whichever it is, we know the system, its purpose, the environment it will operate in, its intended service life, and how it's going to behave. So we want to design and build the system, and we have a good idea about its properties and inputs. As I said, we know which responses we are interested in, and we have a model that relates the inputs and the properties with the response, and we have a good idea about what an acceptable response is. Now, some or all of these quantities could be time dependent in nature, and because we know what the response is and what the acceptable response is, we have a good idea about what constitutes failure. Now, our system does not have to have only one failure mode. There could be multiple performance requirements. For example, even in this very simple case, there could be some torsion and loading, and I would be worried about that. If instead of tensile, the force was compressive in nature, I would be worried about buckling instead. So I know what failure modes there is and how to express them. Now, because of all the uncertainties that we are talking about in this problem, in the inputs, the properties, the models of the system, and something much more difficult if there are missed or unknown modes of failure. There are ways of handling that. And if I know the randomness is involved, how to model the appropriate random variables or random fields and random processes, I would be able to compute the probability of failure or the distribution of the time to failure and its various properties. So with this information, I should be able to take some decisions. Is the failure probability low enough? If not, then I would need to redesign. Is the solution economical? And what would be an acceptable failure probability? If I need to find that out, that would require an additional analysis. In the end, I might also be interested to standardize the process, because if I have to do this over and over again, that would be an excessive demand on my time and resources. So if there was a design guide that would work most of the time in similar situations, then that would be something I would be interested in as well. Now, this is about design of a system that is yet to be built. But once we have an existing structure, some of the concerns and questions are different. The structure is already in place, and the best model of the structure is the structure itself. The uncertainties are there, but now I am able to do some non-destructive measurements, so maybe the nature and magnitudes of the uncertainties are different compared to before. And I would now be interested in this existing system, that it remains safe and serviceable, it is cost effective to maintain, and it lends itself to monitoring. Because I would be interested in the questions is how is its health and how much load it can carry, and for which I might need to do some systematic in-service inspection. If I'm worried about something that might go wrong in the future, that would bring me under preventive maintenance, and I would like to know how much to spend, what to fix, and how often to undertake such maintenance activities. Now, these are all concerns that are relevant for the intact system under normal conditions. What would happen if the system gets damaged for some reason? And then I would have different sets of questions and concerns. Do I repair it or do I replace it? In either case, how much loss or how much downtime would be acceptable? Are there new limit states that are of concern here? For example, I now might be interested in the fracture limit state, which I wasn't before. And because in this new conditions, a new damage condition, I might have different expectations from this damage structure. I might have different acceptable failure probabilities, and I might also have a revised estimate of the uncertainties involved. So putting all of that together, an engineering project, which could just be the concept definition or working through the steps through prototype or production or construction or retrofitting. In any of these cases, I would have a set of functional objectives to meet, and there would be constraints that we have already talked about. And in the end, I should be able to provide a solution in which the objectives are met, the constraints are satisfied, and whatever trade-offs need to be made, they are made. In light of all that we have been discussing in this lecture, it would be appropriate to actually restate the last 3 points of this slide, and which I am now adding in red font, and restate that the objectives are met most of the time, the constraints are satisfied most of the time, and the trade-offs that are made are acceptable. So with these thoughts, let's look at once again the contents of the first part of our course. And as you can see, the first step was to model and estimate the uncertainties. So the next 5 lectures we are going to spend on the theory of probability and random variables. Thank you, and see you there.